Hello everyone, I'm Bhrigurishi Mishra, a PhD student at IIT Bombay, and this is the online session of Elements of Solar Energy Conversion. This is for week 9. So, in this session, mainly concentrating collector used for solar energy conversion has been discussed, and so what is concentrating ratio and the properties of parabolic trough collector and CPC has been discussed. So in this part I am taking care of the portion till which PTC has been covered. So I'll talk about the optical properties of PTC and concentrating ratio. So some questions based on these things, and the other section which is thermal analysis of PTC and also uh, optical analysis of CPC has been covered by the another TA, Mr. Pawan, in Saturday's online session. So this session was supposed to happen on Friday, but due to some academic reason, I postponed it on Tuesday. Okay, so let's start. So the first question is, what should be the value of intercept factor? So there is an intercept factor for this for the concentrating collectors. Okay, so first I want to give you just a brief overview what is concentrating collector. So how this concentrating collector has been used for this solar energy conversion. Okay, so concentrators, so there are two essential things in this concentrating optics systems. One is concentrators, which are basically mirrors, okay, which is used to reflect or refract the incident solar radiation, mainly beam radiation here we are talking about. Okay, and that it concentrated to a receiver which consists of an absorber plate. Okay, so in a simple language, I have a mirror here uh, which and suppose I have a receiver here. Okay, so this is concentrator and this is receiver. This is nothing but a mirror or lens. Okay, so when solar radiation hits the surface, and we basically track the solar radiation. That means we move this concentrator depending upon the position or the path of the sun's movement. So this solar radiation beam when hits on this concentrator, then it reflect and concentrate it to the receiver. Okay, and then receiver has the absorber which absorb it, and then further this absorbed energy has been used for several applications, mainly to produce the electricity. So this so there is an absorber here which absorb this energy, and the temperature of that absorber rises so maximum like 200-300 degrees centigrade, and then there will be fluid, either water or molten salt fluid, which absorb this absorber's heat, and then it is used in Rankine or any other cycle to produce the electricity. Okay, so the first question is, what should be the value of intercept factor? Now what is intercept factor? So intercept factor, so the definition of intercept factor is fraction of radiation. So it is, this intercept factor is the fraction of radiation which is reflected or refracted. In most of the cases we use mirror to reflect the solar radiation to concentrate it on receiver or to send it on the receiver. Okay, this lenses has been used, not generally used. Okay, so yeah, fraction of radiation which is reflected or refracted uh, from the concentrator and is incident on the receiver or absorber. Okay, so this is the fraction of radiation which is reflected or refracted from the concentrator and is incident on the receiver or absorber. So that means so suppose x amount of radiation is hitting to this concentrator, then y amount of radiation, okay, is going to the receiver. Suppose this is x and this is y. So basically intercept factor is y by x. Okay, so now so in the best case scenario, whatever the radiation hitting on the concentrator should go to the receiver. Okay, so that means it should be 1, best case scenario, best case scenario, or ideally speaking, so intercept factor should be 1, and in this way we will gain the maximum efficiency. However, this is not the case always, so depending upon the application, this y is always less than the x. So for example, in central receiver tower where we have this giant mirrors known as heliostats on the field, and then we have a receiver here. So all these heliostats concentrate the incident radiation to this receiver. Okay, that is what is called central receiver tower. So in this case, depending upon the area of the absorber, there will be some spillage, means loss of radiation at the absorber, not due to conduction, convection or radiation, but due to spillage. Okay, and then again so the distance between these heliostats or mirrors and the receiver can be as large as 500 meter. Okay, these are very big plants spread in the acres, okay, acres land. So the distance can go up to 1 kilometer also. So then there will be some air particles, aerosols, water vapor presents in the atmosphere. So when this solar radiation traveling from this mirror to this receiver, it interacts with the air particles or aerosol particles also, and thus some fraction of solar radiation gets absorbed or scattered. Okay, that means it diffuses, so there will be some losses here. Okay, and apart from that, there will be some spillage here at the receiver, and again some radiation and conduction convection losses also occurs. Okay, but yeah, for the best case scenario, the intercept factor is 1 and it should be 1. So we try to minimize this spillage and radiation loss, conduction losses as much as possible. The next question is, which of the following is correct? Collectors with large acceptance angles require only occasional adjustments. Collectors with small acceptance angles have to be adjusted continuously. So what is acceptance angle? First let's talk about acceptance angle. Okay, so angle over which beam radiation may deviate from angle over which beam radiation may deviate. Mr. Sudhakar, could you please mute yourself? Hello. Yeah, thanks. So acceptance angle is angle over which beam radiation may deviate from the normal to the aperture plane and yet reach the absorber. Okay, so suppose I have a collector like this, so whatever the radiation coming in any direction, if although after reflecting to this surface, if they are reaching to the receiver here, okay, then that maximum angle is known as the acceptance angle, and it is denoted as 2 theta a to theta a. Okay, so any radiation, okay, which has any radiation incident within this acceptance angle will reach to the absorber or receiver. So all radiation incident within the acceptance angle is reflected to the receiver. Okay, so that means if the radiation hitting the surface within this acceptance angle, that means you are gaining some heat from that radiation. Okay, so now the question is, collectors with large acceptance angles requires only occasional adjustments. So now this acceptance angle also proportional to the concentrating ratio. So C for 3D it is 1 by sine square theta a. Okay, this is half. So the total acceptance angle is 2 theta a, and this is half acceptance angle, and this is for 3D max, and for 2D it is 1 by sine theta a. So clearly if acceptance angle is large, okay, that means theta is big. So in that case sine theta will also be large, and close it approaches to 1, and thus this concentration ratio is less. Okay, and whereas if acceptance angle is very low, then then this 1 by ratio will be very large, and thus concentrating ratio will also be very large. So both are true. That means collectors with large acceptance angles require only occasional adjustments. Since they already have very large acceptance angle, they can concentrate most of the incident energy to the receiver. Okay, so they need very less adjustment. But if the acceptance angle is very small, that means you have to track them, and it should be for it should like you have to adjust the concentrator continuously in order to match the normal of the surface parallel to the beam radiation radiated by the sun. Okay, so that means both are true. So the correct option is option C. Both A and B are correct. Means large acceptance angle collectors with large acceptance angles require less tracking or very less adjustment, but collectors with small acceptance angles have to be adjusted continuously. So it requires two-axis tracking. Okay. So the next question is which of the following is true in regards to concentration ratio? PTC, so concentration of PTC greater than concentration of CPC greater than concentration of FPC, or CPC greater than FPC greater than PTC, or FPC greater than PTC greater than CPC, or all three has equal concentration ratio. So first let's discuss what is FPC, CPC, PTC. So FPC we have already discussed in previous lectures, but here FPC is with the concentrator. Okay, so FPC is flat plate collector with the concentrator. So suppose I have this is my FPC. Okay, and then I have a mirror here. So what this mirror does is, first whatever, since it is a flat plate, it can take all beam or diffuse radiation, but there will be, so this mirror, what it does is, there are radiation coming to this mirrors, and this mirror concentrates these radiations to the flat plate collector. Thus it gets more radiation and hence its efficiency increases. So this is the flat plate collector, and it requires a very minimal tracking. So it has a very large acceptance angle, and thus its concentration is very low. Okay, so large acceptance angle, and thus concentration is low. CR, concentration ratio, or C, concentration. Okay, and this is non-imaging. Okay, the next is CPC. So CPC is a compound parabolic collector. So this is compound parabolic collector. So it has a shape, it contains two parabolic mirrors, and this is the receiver. So the radiation coming here like this, and whatever it is hit to the surface, it reflected towards the receiver. Okay, so this is also non-imaging concentrator, and the concentration ratio is, it ranges from 3 to 10. Okay, so okay, now the last one is PTC. PTC is parabolic trough collector. It is also called cylindrical parabolic collector, also called cylindrical parabolic collector or concentrator. So it has a concentrator of like this with some arc, and then it has a point or a spherical receiver. Okay, and then whatever the radiation is coming or not exactly spherical, but it may be cylindrical, okay, receiver. So it is directed to this receiver. Okay, so the concentration ratio of this PTC ranges from 10 to 80, okay, which is very high, and it also requires tracking, and it has a very small acceptance angle. Since it has a small acceptance angles, it requires tracking, and as per this relation, this sin square theta or 1 by sin theta a, so acceptance angle small, concentration ratio will be large. So thus in regards to concentration ratio, PTC will have a highest, and then CPC, and then FPC. So the first option is correct. PTC, the concentration ratio of PTC is greater than CPC and greater than FPC. Okay. Now the next one is, which of the following are true? Paraboloid dish collector has concentration ratio ranging from 100 to few thousands and yield temperature up to 2000 degrees centigrade. Parabolic trough collector, linear Fresnel reflector, and Fresnel lens concentrating collector have concentrating ratio in the range of 10 to 80 and yield temperature between 150 degree to 400 degrees centigrade. Parabolic trough collector, linear Fresnel reflector, and Fresnel lens concentrating collector have concentrating ratio in the range of 1000 to 80,000. Paraboloid dish collector has concentration ratio of 1 lakh. Okay, so first these are very high concentration ratio. So first let's see whether this high concentration ratio is even possible or not. So the maximum concentration ratio is between the sun and the earth, so that the theta for that is around 0.267. so for 2D this value is around just a minute. Okay, I forgot to write the exact value, so we can calculate it here. Anyway, so this C max is around 200 something, okay, and this C max 3D is 45,000. okay, so this is the upper concentration limit. So any 3D concentrator cannot have cannot have concentration ratio greater than 45,000, and here it is saying 80,000, so this is not the correct answer. And also this paraboloid dish collector has concentration ratio of 1 lakh, which is also not possible. Okay, now we need to check this AB. So first what are these terms? Linear Fresnel reflector, so it is nothing but, so we have very small like we have this kind of reflectors here, and they reflect the radiation and concentrate it to a receiver. This is also known as LFR, linear Fresnel reflector. For the Fresnel lens, we have this giant lens which concentrates the radiation to a point by using refraction. So this is Fresnel lens collector, and this last one is this paraboloid dish. So paraboloid dish has the structure of this, so it contains this paraboloid dish like this, and the receiver is, this is the point receiver here. So whatever the radiation is coming is reflected to this receiver, and it has very low acceptance angle. So very low acceptance angle, then thus it requires tracking. So its CR is in the range of so it can go from 100 to thousands, like 1000, 2000, sorry. So it can go from 100 to few thousand, that means 1000, 2000, or even it can go to 5000 or 10,000. Okay, and due to such high concentration ratio, it is also able to get a very high temperature. Okay, around 2000 up, like it can go up to 2000 degrees centigrade. So this first option is true. Now talking about second option, so this uh, parabolic trough collector, PTC, LFR, and this Fresnel lens all has similar concentrating ratio, that like they have ratio in the range of 10 to 80, and due to this concentrating ratio, they can provide a temperature between 150 to 400 degrees centigrade. So this is also true. Okay, so A and B both are true in this case. Now next question is find out the concentration ratio of 2D and 3D concentrators if acceptance angle is 28 degrees centigrade. So as I wrote earlier, that so C max 2D is 1 by sine theta A, and C max 3D is 1 by sine square theta. So here acceptance angle is given. Please note that it is given acceptance angle, and here we use half of the acceptance angle. So 2 theta is given as 28 degree. Sorry, not, this is not the Celsius. Okay, this is just 28 degree. Okay, so 28 degree, so theta is 14 degree. So we can calculate C max 2D. Just a minute. So yeah, we can calculate this concentration maximum concentrating ratio for acceptance angle of 28 degree. So C max 2D, it is 1 by sine 14 degree. So 1 by sine 14, so this is around 4.133. okay, and for 3D, C max 3D, this is 1 by sine square 14 degree. So this is 1 divided by just a minute. So 1 divided by sine 14, so it is around 17.086. okay, so obviously 3D has a higher concentrating ratio compared to 2D. okay, so because I mean this is obvious that C max 3D is just the square of C max 2D. okay, so the next question is a perfect parabolic trough collector has an aperture of 7 meter and a focal length of 6.53 meter. The angle phi is 10 degree. It is long in the z direction, so that end effects are negligible. So calculate rim angle, rim radius, local mirror radius, and dimensions of an image if receiver is cylindrical or flat. Okay, so first let me draw the diagram for this parabolic trough collector. So suppose I have this concentrating reflector, okay, and this is the focus F. So this is R. Okay, this R is known as the local mirror radius, and this is RR, rim radius. Okay, and this angle is phi r, and this angle is phi. Okay, A B, and this is a by 2, where a is the aperture. Okay, and the distance between this is f, focal length. Okay, so a is aperture, f is focal length. So aperture is given as 7 meter and focal length is also given as 6.53 meter, and phi is also given as 10 degree. So what are the things we need to calculate? We need to calculate rim angle, that means which is phi r, rim radius, that means rr, local mirror radius, that means small r, and also we have to find out the dimension of the image if receiver is cylindrical. So if receiver is cylindrical, the image will also be cylindrical, and then we have to calculate the diameter of the image. Okay, and for the flat we need to calculate width of the image, that is W. So okay, let's calculate. So first a rim angle. So the formula for rim angle is tan phi r equals to 8 f by a by 16 f by a whole square minus 1. Okay, so we have f here 6.53, a 7. So the ratio of f by a is nothing but 0.933. So we can calculate phi r easily. It is tan inverse 8 into 0.933 divided by 16 into 0.933 whole square minus 1. So if you solve this, it turns out that phi r equals to 30 degree. Okay, now we need to calculate second is rim radius. So B is rim radius, that means RR. So how to calculate rim radius? Okay, so sine phi r is a by 2 times RR. So this goes RR equals to a by sine phi r. Okay, so here a is 2 times, so here a is 7, and sine phi r, that means sine 30 is half. So that means this radius is also 7. Okay, 7 meter. Now the third one is local mirror radius r. So the formula local mirror radius r is 2f by 1 plus cos phi. Okay, so we have already given phi equals to 10 degree, so we can put all the values. So f is given 6.53, 1 plus cos 10. So if we solve this, r will get 0.658 meter, or okay, so local mirror radius is 0.658 meter. Now the d. Okay, so first, if it is cylindrical receiver. Okay, so for the cylindrical receiver, the diameter of image d is 2 rr sine 0.267. If you solve this, it comes 0.0652 meter, which is 6.52 centimeter. Okay, and the second one is flat receiver. So for flat receiver, we have width of image, and width of image is w equals to 2 rr sine 0.267 divided by cos phi r plus 0.267. Okay, so and if you solve this, you'll get 0.0755 meter. Sorry, this is meter, so it is 7.55 centimeter. Okay, so in case of flat receiver, the image the width of image is 7.55 centimeter, and in case of cylindrical receiver, the diameter of the image is 6.52 centimeter. There is a third one, that is semicircular. So for that you have to calculate minor axis and major axis, that you can check. Also there is one thing, as this rim angle increases, okay, so what will happen to the the image, okay, diameter, or the receiver will have a high or the dimension of image increases. Okay, so this we can check here. So it is here cos phi r. So as phi r increases, this cos will decreases, and thus width of image will increases. Okay, that you can check. So yeah, that's it for today. So we will meet this coming Friday, and then we will discuss some problems for this week's content, that means week 10. Okay, so thank you.